So good morning, everybody, to this second day of SALTOpower Fast Track School. Welcome to all the participants here in present. We are very sorry for the weather. We hope that we will get well soon for this afternoon for the visit to the infrastructure and facilities. And very welcome to all the online participants. I would like to remind you that all the questions will be answered in the section question and answer, not in the chat. So please consider this tool of Teams. So I would like to show you the agenda of the second day. So I'm going to introduce you the first speaker of the first lesson of today. That is Luca Turchetti. Luca Turchetti is a research engineer at the Solar Thermal Energy and Smart Network Division in ENEA. He is a chemical engineer and holds a PhD in industrial chemical processes awarded by University of Rome La Sapienza. He has more than 15 years experience in fundamental and applied research and academic teaching in the field of chemical engineering and renewable energy, with the specific focus on concentrated solar thermal technologies, such as thermal energy storage systems and innovative chemical processes supplied with high-temperature solar heat. Since 2020, he sits as Italian delegate in the Executive Committee of Solar PACES, the technology collaboration program of the International Energy Agency devoted to solar power and chemical energy systems. So please, Luca, you can start.
Okay. So here we are. Sorry for this little inconvenience. Good morning, everybody. Good morning to the attendees who are here in presence. Good morning to the people connected remotely. Thank you, Arna, for your introduction. So I'm gonna talk today about the use of molten salt as heat transfer fluids for chemical reactors. I would like to start this talk by building on some key messages that were delivered yesterday during the school. And the first message is that, as you see here, you see this first message in this pie chart, which was shown yesterday during one of the presentations. And this pie chart tells us that in 2019, basically nearly 1/3, nearly 30% of the world energy consumption was related to industrial uses. And out of this share, roughly 70% is related to the use of heat, energy as heat, not as electricity. So this somehow may question the mainstream narrative that if we want to decarbonize our energy systems, we have to electrify everything. Why this? Because while it is rather easy to electrify using specific sectors, it can be much more difficult in this industrial sector, especially when it comes to high temperature heat applications. It is indeed evident and clear that electrification is playing a major role in the decarbonization of all sectors, and also in the industrial sector. We're moving toward a shift of the type of processes which are being modified in order to be electrified. But this is for sure a slow process and a very difficult process. Again, when we talk about high temperature heat applications. So why is in general decarbonization associated with electrification only when we need today so much heat in our final energy consumption? Well, I would say that this is mostly related to the fact that there is an underlying idea that only electricity can be renewable energy, while heat is necessarily obtained by fossil fuels. And here comes the second key message that was delivered yesterday. There are today technologies, renewable energy technologies, that are able to produce renewable heat and not power. And concentrated solar thermal technologies are respond to this definition. You've been explained what concentrated thermal technologies are. So you know that basically they produce in the first place heat, which can be turned into power, of course, through power cycles. And in this case, we talk about concentrated solar power application, CSP. But there are concentrated solar thermal is much more than that. You can use this heat for decarbonizing many different types of final uses, like the sector industrial and residential heating and cooling applications, the sector of fuels. You can desalinate water, just to provide some examples. And of course, you can contribute to the decarbonization of the energy production sector. Another key important key feature of this technology, which was highlighted yesterday, is that today CST can rely on commercial solutions for long-term storage, which in the current installations can achieve up to 17 hours of operation at rated capacity, and which basically can sustain the supply of renewable heat also around the clock operation, which is key when we deal with chemical processes. And so now let's focus on what is the core of this presentation. So how do we bring solar heat to the core of chemical processes, which are, by the way, chemical industry in the industrial sector is one of the industries that consumes the higher amount of heat. So it's very important to achieve this target. How do we bring solar heat to chemical processes? And I would say to the core of chemical processes, because you can integrate the heat at different levels in a process with, let's say, more or less conventional exchanges. But we want, in this case, the topic of this presentation is delivering the heat to the core of the process, that is to the chemical reactor. What are the approaches that follow today? A first approach is the use of irradiated reactors. So we put the reactor on the focus of a concentrated solar system. And this can be done either directly, which means we directly expose the reaction medium to the concentrated solar radiation, and we flow. The reaction medium can be a catalyst, can be a reactant solid, and we most likely also flow. It's not necessary, but very often it happens that we flow a heat transfer fluid or a reacting gas through the solid and so on. But the point is that we deliver concentrated solar energy directly into the reactor medium by putting reaction medium by putting the reactor on the focus of the system. A similar but somehow different approach is the use of indirectly irradiated reactors. In which we put the reactor in the focus of the system, the concentrated solar system, but the reaction medium is not directly irradiated. There is, for instance, a reactor wall in between, and then you have indirect re-radiation from the reactor walls to the reaction medium. There are pros and cons, of course. In this case, you will need a transparent window, typically a quartz window, which entails some difficulties, but for the construction of the reactor, and also some limitation in the sides, some problems with the robustness of the reactor. But on the other hand, you have a more efficient delivery of the solar energy to the reaction medium. Also, direct and indirect irradiation can be applied to process streams, not directly to the reactor, but also to process streams, like, for example, for preheating the feed stream upstream of an adiabatic reactor. This is just an example. However, as you see here, we're talking about molten salts here. I don't see an application for molten salt in this type of reactors. We are delivering solar radiation directly to the spot where we need it. Another approach, which can be followed to use molten salt for this application, is the use of heat transfer fluid. So in this case, I'm showing you this scheme that was developed for solar heat for industrial process applications that describes more or less all the possible integration point of solar heat inside a process. And you see that you have here, we're not gonna go into the details of the scheme, but you see here you have your process. You have a supply line, which is basically the process, heat transfer fluid, and you have the solar system, solar energy collection system, and you will have the use of a solar heat transfer fluid, which can bring the solar energy into the process at different integration points. So you can, for instance, you can heat the process heat transfer fluid with the solar heat transfer fluid. Sometimes the process is fluid and the solar heat transfer fluid can be also the same, which it is very convenient in some cases, which I'm going to show you right away. But and also, and which is most interesting for us today, is the integration at the process level directly into the process vessel, which is the reactor. And we're going to focus on this case because definitely this is the most challenging case, because you need to develop integrated heat exchangers reactors. So you collect solar heat into a heat transfer fluid, you bring it to the reactor, but you will have to develop a specific unit which will be able to carry out the reaction, the process, and receive the solar heat from the heat transfer fluid. So let's compare these two different approaches. All have pros and cons, of course. Let's start with the operating temperatures that we can achieve when you go for direct or indirect irradiation. Irradiated reactor, we can achieve very high temperatures, which are basically limited by your concentration systems or concentration systems, and of course to the resistance and features of the materials that you're using. These in current applications, which are not industrial but research application, either high TRL applications, but still research, can achieve even temperatures above 1000 Celsius degrees. When we use an HTF, heat transfer fluid, the maximum temperatures is limited by, of course, the stability and applicability of the heat transfer fluid. And when it comes to the current molten salt mixtures that are used in CSP plants, this is below 600 Celsius degrees as wall temperature, which means that bulk temperature in current installations up to 565 Celsius degrees. Also, it's possible to use gaseous heat transfer fluids. In this case, there are basically no temperature limits, but there are many issues to be faced related to the poor heat exchange properties of gases in general, and especially low pressure gases, which are today used in these applications. Solid heat transfer fluid, which means fluidized solids on particles, which are a main topic, very current topic today in CSP, in the CSP field. Also allow for high temperature, but also they have some major challenges in terms of heat transfer equipment, which are, by the way, being dealt with right now in several research projects worldwide. So I'm not saying you that this is a current problem and we're working to solve it, but this is the picture today. We can go about those temperatures. So other aspects, the use of thermal energy storage systems, which is key for chemical processes, as I told before. When we deal with directly irradiated reactors operating very high temperature, this is really today it's not a commercial solution. There is not a commercial solution for that, because there is not a commercial solution for very high temperature storage, thermal storage at the moment. There are several research prototypes, but still there are many issues to be solved. While if we move to the use of heat transfer fluid, we can rely on a more consolidated approach, which is common in the process industry. And basically, the design of the equipment is much closer to the case of conventional equipment. So this is, of course, a good point. When it comes to heating solids, direct irradiation is more efficient. You don't have indirect, the use of a transfer fluid will entail some temperature drops and less efficient heat transfer. regarding the design of the key piece of equipment, the reactor itself, the design of receiver reactor is very challenging because you have to combine 3D simulations of which combine optical properties, simulation of the solar radiation, ray tracing simulations inside the reactor with the thermal and heat transfer, mass transfer, and so on. So it's very challenging. While in the case when we use a heat transfer fluid, the design, as I told before, is closer to what we do for a more conventional, I'd say another reactor using another more conventional heat transfer fluid than the molten salts. When it deals to the management of cloud transients, also this is a key issue in because we want to ensure that our user or process is fed continuously with a firm energy supply. It's much more challenging to deal with an irradiative reactor, which will immediately be affected by the passage of a cloud. While if we, of course, the user of a heat transfer fluid ensures us to have a buffer, thermal buffer, which will also buffer fluctuations in the availability of the solar fluid. Same applies to the startup and shutdown operation. If we use a molten salt or any other heat transfer fluid in our reactor, this can be used also to keep the reactor warm during the standby periods, which means that it will be also easier. You can have hot standby operation of the reactor, which means that we will more easily and readily put the reaction back in operation after a shutdown of the system. Okay, so now that we have this picture clear, we may say why we have to limit to solar. Up to this moment, I said delivering solar energy to solar heat to chemical processes, but the picture is wider than that. We can apply the same logic and then use molten salt to deliver solar heat produced with other renewable energy sources and other renewable energy technologies. So here you see a scheme that somehow summarizes the vision, which is also the vision of the project that provides the framework in which this school is developed. The SALTOpower project, molten salt can act as a link to energy, renewable energy produced in many different ways, and link these energies to commercially available today thermal energy storage solution and supply a chemical process with renewable heat. You can also combine, of course, you can select just one or combine different technologies in this case. So let's move to the to some examples. I selected two case studies. I will focus mostly on the first one, also because I think I'm not sure I'm gonna have much time for the second example, actually. So the first example I want to present you is related to the I would say the most important process that we use today to produce hydrogen. Hydrogen is another key enabler of the energy transition. So I think it's very meaningful and current example. And hydrogen today is mostly produced by the so-called steam methane reforming process. The hydrogen produced by this process is today called gray hydrogen. And the color gray lets us understand, which is not very good for the environment, actually, because basically the steam reforming is a set of also a complex set of different reactions. I would say the most important one is the one you see here. You combine methane with steam and high temperature over a catalyst, and you get carbon dioxide and hydrogen. This process is strongly endothermic, which means that it requires a lot of heat to be carried out. So in the end, this process today is associated with big emissions of CO2, both because CO2 is produced as is contained in the flue gas of the combustion process we need to produce the process heat today, to run the process today. And because CO2 is also a product of the reaction we are carrying out to produce hydrogen. This, in the end, leads to the production of up to 8 to 12 kilograms of CO2 per kilogram of hydrogen produced. So it is clear that we cannot continue to rely on this type of processes in the future to produce hydrogen if we want hydrogen really to be a clean energy vector, a green energy vector, and a key element for the energy transition. Other aspects of this process, the operating conditions are up to between 700 and 1000 Celsius degrees. It's operated at between 10 to 40 bars. It requires steam as reactant, which is, of course, an energy-consuming element for this process. And the price is, today, this is the benchmark of the hydrogen production price, which is between $1 and $2 per kilogram of hydrogen, but this is strongly, very strongly related to the gas prices. And we know by personal experiences that these prices can be rather volatile. So this is also another issue that must be fixed. So how can we feed this process with solar heat? And I will focus on the use of solar salt, which means a mixture that can operate, can be heated, as we told before, up to 565 Celsius degrees as bath temperature. I'm going to report about the experience of a research project that was concluded some years ago and carried out coordinated by ENEA. The project was called Cassaccia, and the aim of this project was to power steam reforming with solar energy, which in the first place requires lowering the operating temperature of reforming, because otherwise we won't be able to couple it with the solar source with solar salt. So the aim then is to shift the operating window, temperature window, in the range between 450 and 550 Celsius degrees. There are, of course, a number of advantages in doing so. You can use lower grade materials. You have higher safety of your process. You can use okay, this is very specific. I'm gonna skip it. You need to know the process. You can use one reactor less. You can use, instead of 2 reactors, 1 single reactor to carry out the whole process. And which is most important for our presentation today, you can use solar power from CSP or CST installations with molten salt. And you can achieve up to 100% renewable hydrogen if also your feedstock, your carbonaceous feedstock, is renewable. For instance, you can use methane, not fossil methane, but methane from biogas. Or even if you use fossil methane, only by replacing the CO2 produced, avoiding the CO2 emission due to combustion, but also by replacing the heat supply with renewable energy, you can achieve reduce the CO2 emissions. Of course, there are several drawbacks. The first one is the low hydrogen yield, which is addressed, as we're going to see right away, with a membrane reactor. You get slower reaction kinetics compared to the conventional process. And then you have to develop active and stable catalysts also this in this lower temperature range. You also need a very a reactor bed, a catalyst bed, which is very effective in transporting heat, because ensuring a good heat transfer and uniformity of temperature in the bed of the reactor is especially important in the case in which the reactor operates at lower temperature. So the reason why you operate this process at 700, 1000 Celsius degrees conventional is because otherwise you get a very low hydrogen conversion, which is not industrially feasible. So how do we manage to operate with a reasonable conversion, this process also at lower temperatures? By the use of a membrane reactor. What does this mean? This is the process, the steam reforming process. You see, you have methane and water, steam and high temperature, and you produce hydrogen and carbon dioxide. And the first part of the reactor, this is what happens. You mostly produce hydrogen. Only the forward reaction, of course, but this is an equilibrium reaction, which means that as the products are present in the reaction mixture, the reverse reaction will start, and you will achieve an equilibrium point with a given conversion method, which means a a given percentage of the methane that you're feeding that is actually converted into hydrogen. At low temperature, this conversion is very low, from 10, 20, 30%, the maximum in the best feed conditions. While for this process to be industrially applicable, you want to go to higher conversion. So how do you manage that? You introduce in the reactor a membrane, a nitrogen permeable membrane that allows the passage only of hydrogen, and you remove hydrogen from the reaction space. This will push the forward reaction and allow you to achieve higher conversion. In order to enhance hydrogen transfer across the membrane, it is usually, this is not necessary, but usually you also include a sweep stream, typically steam, or you can use also nitrogen, but it would be difficult then to separate the hydrogen from the nitrogen. And another advantage, so this way you can achieve high conversions also at lower temperatures. And another advantage is that what you will, your product hydrogen is here. You have also very pure hydrogen here because these membranes are very selective. And your retentate, which means what remains upstream of the membrane, it's also a concentrated CO2 stream and water, and depending on how much, on the extent of the reaction and permeation, can contain some residual methane and hydrogen, but it's very concentrated in CO2, which also means that if you want to capture this CO2, this is facilitated. So you have several advantages. So this is the Cassaccia project plan concept, and you see basically here you have the core of the process, which is the membrane reformer, and you use a concentrated solar thermal system to work with solar salt, which are used to provide the process heat to the reactor, and also the heat required to produce the steam, the reaction steam, which is needed to the reactor. This is a scheme of the molten salt heated membrane reformer that was developed for this project. As you can see here, it's basically a shell and tube configuration. It is very close to a shell and tube exchanger, and where molten salt are flown in the shell side of the system. And in the tube side, you have a tube-in-tube configuration where you have an annular space where a reaction is carried out, and the membrane is an inner tube inside the reaction tube. But probably this is clearer if we see these pictures of the reactor before being installed in the plant and being, of course, covered with insulation, which wouldn't allow us to understand what this system looks like. So here you see the reaction tubes. Okay, so this is the tube sheet basically of the system. What you see here is the membrane, which is a tubular membrane, and what you see here is the catalyst, which is a monolithic catalyst over a silicon carbide foam, deposited over a silicon carbide foam, which ensures activity of the catalyst, and also the silicon carbide foams ensures good heat transfer properties across the bed, the reactor bed. Okay. So these are some pictures of the pilot plant, which we installed, and a scheme. The pilot plant, we didn't test this system on sun, so we simulated the solar field by the use of molten salt circuit, which is a facility that you're going to visit this afternoon, that we have here in ENEA, which is basically a system that allows you to get streams of molten salt at a given temperature and flow rate, and in order to test several elements and components, like for instance the reactor that we have seen right here. Quanto? So 40. Okay. So I'm gonna skip the second case study, which is less relevant. We're gonna keep it on the slides, but we'll want to conclude on this example, which is more important. Here you see some data about the testing that we carried out on the facility, and I just want to focus here on this plot here, in which you see we carried out long time on streams test. Here you see what is the conversion of a conventional reformer that was placed upstream of our membrane reformer. also this conventional reformer was supplied with solar heat, but it did not have any membrane in it. So what you see here, this feed that we had for the reactor, the conversion was around 30%. Around 30% of the methane we fed was converted into hydrogen and carbon dioxide, which is basically what the dashed line is the thermodynamic limit if you don't put a membrane at those temperatures. So it's very low. And here you see the conversion you get with a membrane reactor, which is basically almost double of that of a conventional reformer. So you can see, and you achieve reasonable values that can be even higher if you tune the operating conditions of the system, which can really allow you to apply this solution for industrial hydrogen production. Here, just very shortly, some recent development. We're also trying to develop a planar version of this membrane reformer, which would entail some advantages in terms of compactness, modularity of the system. It's like moving from a shell and tube exchanger to a plate and frame exchanger. However, using this type of configuration with molten salts is very challenging. So we are still deciding whether it is better to stick to the shell and tube configuration. And I would like to conclude with some of the lessons learned with this experience, especially what are the main challenges that you get in designing a molten salt reactor like this, a molten salt heated reactor like this. Of course, this also applies to a molten salt cooled reactor, because you can consider an exothermic process in which your heat transfer fluid collects the heat, removes the heat from the reaction medium. So we have mainly two types of challenges. One type is non-molten salt related. It is a type of challenge you get for every heated and cooled reactor with the use of a heat transfer fluid, is that you have to correctly design the system to effectively couple mass transfer, heat transfer, and reaction kinetics. In this case, you have three phenomena. You have reaction kinetics, you have heat transfer from the molten salt to the reaction medium, you have hydrogen transfer across the membrane. You have really to select the material properties and to tune in also the reactor sizes in order that you don't have any bottleneck between these three phenomena which all contribute to the final conversion of methane into hydrogen. So other specifically molten salt related issues are, you're going to go into more details about these issues later today with other lectures devoted to the molten salt systems. Of course, you have to, this is also mostly related to the executive design and layout of the plant, while the first type of issues is mostly related to the process design of the reactor. In this case, you have, of course, ensure easy and fast molten salt drainage for this. In case there is, for instance, a circulation pump failure or any other system failure that requires to shut down the system, you must be able to very quickly and easily drain the whole system from molten salt. Otherwise, you can end up with freezing molten salts inside the reactor, which means that you will probably not be able to use the reactor, or you will have to, it's going to be very complicated to melt the salts from this type of systems. This entails accurately designing the pipeline slopes and the curvature of the pipes, because you have to avoid stagnation points in which, when you drain the system, salt can be collected. You have to reduce any flow restrictions because you don't want pressure drop. The drainage must be very fast. Of course, then you must be sure to correctly design the thermal insulation of the system and to trace heat the part of the plant which are called the temperature, because you have some part of the plant sticking out, like also some instruments are sticking out of the insulation, which act as a fin for heat exchanger and cause lower temperature in the plant. So it's very tricky. You must be where molten salt can in the end solidify in case of any inconvenience. So these are the main aspects you have to consider. So I will skip this second example because I definitely run out of time, which is another example related to hydrogen production with an innovative electrolysis process. But in this case, coupling with molten salt is less challenging than the previous cases. Probably is less relevant for this lecture today. So that's it. I thank you for your attention. And of course, if you have any question, I'm glad to get them now. Also, for the people connected from home, I remind you that if you have any question, you can write it in the question and answer section. Of course, you can also send me an email, and also a question that we don't have the time to reply now, we can reply later by chat. And any questions from the audience here?
I think that it's a good idea to use the transfer fluid in the cold storage because directly the receivers. I think for chemical process it's challenging because chemical process not like to run 24 seconds. So, and as a question, do you see any other interesting processes for molten salt which could be supplied by molten salt and the two examples you showed?
Okay, so I'm going to repeat the question for people at home. It was pointed out that indeed we have using irradiated reactors can be an issue to be used when coupled with the chemical processes, because chemical processes really like to work steadily in steady state conditions. What are the, it was also asked, what are the other processes that can be supplied by this type of systems? There's a huge amount of processes. You go from, by changing the mixture of molten salt, you can also go to lower temperatures. Because if we go above this type of, source salt can be used up to 565 Celsius degrees, which means what is called in the process, the solar process applications, solar heat applications for heat, is called high temperature. So in this case, you get processes from the paper industry. There are some processes also for at lower temperatures for food and beverage. And if we also develop other molten salt mixtures able to go even higher than 565 Celsius degrees, then in this case, the range of opportunities is much wider. So definitely there are, I use this example because of course, this belongs to our personal experience in the research, but also because it's a hydrogen production process, which is very current, but you can apply these also to other processes for again, the food and beverage, paper industry, ceramics. There are some parts, most part of processes in the ceramic industry are carried out at very high temperature, but there are also processes that they need a lower temperature. And so, yeah. Any other questions? Does not seem the case, so I thank you again for your attention, and leave the floor to Anna for the rest of the school.
Thank you again, Luca, for a very interesting presentation. So I would like to move to the second speaker of today, is Radia El-Kadi. Just a brief introduction. Radia is a young researcher at the Renewable Energy Chair of University of Évora. She did her PhD in thermodynamics and energetics, focused on the linear concentrating solar plant technology coupled with the cogeneration for waste heat recovery. She's currently a researcher in the field of high and medium temperature application of solar thermal technologies, and she's mainly working on technology transfer and applied research activities in thermal energy storage, solar heat for industrial processes, concentrated solar power, thermal and hybrid storage concept, system simulation and integration commissioning, and operation of thermal system using molten salt as heat transfer fluid and heat storage media. So please, Radia, we can move to your presentation.
Sure. Thank you so much. I'm happy to be here today and presenting you the molten salt potential in the Carnot batteries concepts. I will start with a brief introduction about about the Carnot battery concept, presenting the advantages and disadvantages of the system, followed by the key factor for the Carnot battery performance. And before concluding with the Carnot battery competitiveness, I will just briefly talk about the multi-site mixture that could be used in these concepts. So talking about the Carnot battery, there are an energy storage solution where electricity is stored as thermal exergy. The Carnot battery mainly is comprise a set of multiple technologies which have a common underlying principle of converting the electricity to thermal exergy, storing it in thermal energy storage systems, and in a time of need, converting the heat back to electricity. Currently, the concept is known under Carnot batteries and pumped thermal energy storage. Back to the concept and the working principle of the Carnot battery. The working concept is first an input, which is an electric energy, is used to create a temperature difference between low temperature and high temperature reservoir. And this way, the storage is charged and the electrical energy is stored as thermal exergy. As the heat is flow from the low temperature to the high temperature reservoir, the storage is charged. The stored thermal exergy can be discharged in the form of a heat, allowing it to flow from the hot temperature tank to the low temperature tank again. During this discharge phase, the heat flow is used to power a cycle, which converts the thermal exergy to work again. This Carnot battery can be designed with or without a heat pump. In the case of designing the Carnot battery without the heat pump, it could operate like a typical heat engine. But in this case, the Carnot battery will be limited in terms of temperature difference between the two reservoirs, the high and the low temperature, and the losses as well. In the other side, we can design the Carnot battery with a heat pump, which can help the system achieve higher efficiencies. But of course, this addition of the heat pump to the system could increase the complexity and the cost, of course. Just to give some examples of the application and the possible integration of the Carnot battery, I presented here a figure that shows that the integration to the power integration to the Carnot battery could be from renewable energy source, in the purpose to increase the flexibility of the plant. The integration also could be from geothermal industry waste heat to be used in the end part to district heating or process heat, for example. Some of the advantages of the Carnot battery are its flexibility, because it could be designed to store energy from a variety of sources. This is the case of Carnot battery, as Luca was presenting before, that this could be used for chemical processes as well. This is also the case for the Carnot battery. It could be a multiple vector energy management because it uses the power, it could be used for power balancing. And also it presents a very flexible aspect to be scalable, up or down to suit different applications. Of course, every system, as it has advantages, it has disadvantages. One of it is the complexity of the system, especially while adding the heat pump to the system, the cost, of course, and the temperature, which limits the performance in certain situation. Also, the efficiency of the system could be limited by factors such as heat losses and so on. Back to the concept of the Carnot battery, we have the first transformation to charge our thermal energy storage that could be via heat pump using Rankine cycle, Brayton cycle, or any other concept to convert the power to heat, or simply using direct resistance. The storage is possible using sensible latent heat or thermochemical options. The last part of the transformation to discharge the system, it could be using the different cycles as the CO2, Stirling, or other options. As any other storage system, the Carnot battery is defined by its round-trip efficiency, which is the electricity produced during the discharge phase and the electricity consumed during the charge. This round-trip efficiency is directly affected by the key component of the system, which are the charging, discharging cycle, the working fluid used in this in the both transformation phase, the thermal storage technology, and also the storage media used, and the heat exchangers. Just to give an idea about the round-trip efficiency, I'm presenting here a list of commercial development projects in Carnot battery. Just taking as an example the three first combination that use the same charging method and discharging method. The round-trip efficiency could be between 25 to 40% in the case of using volcanic rocks and the graphite aluminum alloys at temperature between 600 to 700 degrees. Also, the molten salt as a thermal energy storage could be used, and it gives a round-trip efficiency around 40%. Taking the same, more or less the same configuration, keeping the molten salt in the thermal energy storage and the steam cycle in the discharging phase, and adding only the CO2 Brayton cycle to the charging part, the round-trip efficiency could increase to 62%, which gives molten salt a very important technology to be used in Carnot batteries. The molten salt can cover a really important margin of temperature from 150 degrees till 650 degrees, and this could be presented via different mixture of molten salt, as already presented in yesterday presentation. I have just here some different mixture of molten salt that could be used with different composition. with nitrate based and chloride based that can cover a really important margin of temperature to benefit from the advantage of using molten salt as a phase change material, or using it as sensible heat as well. And just to conclude my presentation, the competitiveness of the Carnot battery, while it may not be the most competitive option due to its complexity and the cost, but it depends on specific application and the trade-off between the efficiency, the cost, and scalability of the system. And by this, just presenting some references that I use for this presentation. And by this, I finish my presentation. Thank you for your attention. Any questions?
But I made this question already. I could see, I don't know if you get quite that, because there is one of the experiments reports in the paper as a negative from the rest.
No, actually, it's not a negative, it's approximately. Yeah,
Makes sense. Usually what makes a negative.
No, it's not a negative.
Okay, so we can introduce the third speaker for today. His presentation will deal with molten salt suitable components, requirements, and operation. So Marco Dauria. Marco Dauria is a mechanical engineer, and he received his PhD in materials and structures engineering at University of Naples, Federico II. It has been working in ENEA since 2019 in solar thermal, thermodynamic, and smart network divisions. His current activities concern modeling and simulation of CSP components and systems, development of CSP performance models, and techno-economical analysis of solar heat for industrial process case studies. So please, Marco.
Thank you, Nakada, for introducing me. So let's go. My presentation will concern molten salt suitable components. We will take a look at the molten salt CSP plan, and we can identify three main components: receiver tubes, tanks, electrical heating system, and then the conclusion. Okay, in this sketch, we can see a LAN-focused CSP plant, and we can identify different main components. First of all, we have the solar field, and that is made up of concentrators that are the mirrors and the receivers, tube receivers. And we can identify the thermal storage. In this case, we have a double tank directly connected to the solar field. Another big component is represented by the piping. And finally, we have an interface between the solar plant and, in this case, with the power block. That it can be an heat exchanger or a steam generator, depends on the cycle we are considering. So the use of molten salt has several benefits. The first one is the possibility to work at high temperature in the solar field between 550, 560, if we consider a binary mixture salt. And this way, we can increase the efficiency of a thermodynamic cycle. Moreover, we can enhance the integration of TESS into the plant because the heat exchanger between the TESS and the solar field, as we have just seen in the previous sketch, are no longer needed. Molten salt have high density, high heat capacity, high thermal stability, even at elevated temperature. These properties are important future for the heat transfer fluid. Compared to the thermal oil, parasitic pumping losses are lower with molten salt because the volumetric flow and the pressure drop are lower. This is another benefit, obviously, of using molten salt in the solar field instead of the thermal oil. However, working with higher temperature higher than 400 degrees, with the current molten salt require the use of stainless steel in piping, vessel, and other elements, since the corrosion issues are well known when carbon steel is used for sodium and potassium nitrates at this temperature. So we can see that the first important component of a solar plant is a component with highest technological content, and the performance, the CSP performance, strongly depends on the receiver tube efficiency. And in the case of line focusing solar plant, the tubes are placed along the focal line of the parabolic mirrors of the Fresnel field. So the heat thermal fluid flow through the metallic pipe to collect thermal energy absorbed by the selective absorber. So metallic pipe needs to fulfill several requirements that are good thermal conductivity to transfer the heat collected by the selective absorber, good mechanical properties to withstand high temperature and operation pressures, good corrosion resistance regarding heat transfer fluid employed in the system. Hence, AEC 321 stainless steel is commonly used in molten salt receiver tubes. Then we have a pipe in borosilicate glass with a film to reduce the reflection losses in the glass, increasing the optical efficiency of the tube receiver. The glass cover is connected to steel pipe using metallic expansion below to compensate different linear thermal expansion of the glass and steel when the obviously solar receiver is working at nominal temperature. The glass to metal welding is used to connect the glass cover and the flexible billows, and is shielding from concentrated solar radiation to avoid the thermal and mechanical stress that could affect welding performance and durability. For the highest performance receiver tube, vacuum is established in the annulus between metallic pipe and glass to reduce thermal losses. So now we consider the model of a receiver tube in a steady state condition, one-dimensional analysis, and we have that the solar energy is absorbed in part from the glass envelope and mainly absorbed by selecting coating. A part of this absorbed radiation is transmitted by conduction through the tube thickness to be finally collected by convection by the heat transfer fluid. On the other hand, there is a radiative and convective heat exchange between metallic wall, outer metallic wall, and the glass pipe. So this thermal energy then passes through the glass envelope by conduction. Finally, there is a heat loss towards the environment by convection and radiation. The absorbed energy, so QAbs, by metallic tube depends on absorbance of a selecting coating. And this can be considered constant with the temperature. And while the radiative loss from metallic tube depends on emissivity of the selective coating. But what happens if we apply vacuum inside the annulus? We can neglect the heat loss, and we improve in this way thermal efficiency of a receiver tube. So commercially, solar receiver tubes are available with excellent photothermal efficiency, absorbance greater than 0.96, emissivity in the range 0.085, 0.095 at 400 degrees, and gustability over long periods, that means 25 years, but operating up to 400 degrees. Only a few products on the market, shot PTR 70, UVAC 3, are suitable for high temperature, above 500 degrees, for application with molten salt as a heat transfer fluid. So the only coating with known photothermal performance at 550 degrees and proved thermal stability for a lifetime on 25 years has been developed by ENEA using the technology of double nitride cermet acquired and commercialized by Archimedes Solar Energy. The solar absorbance of this coating is equal or greater than 95%, while the thermal emissivity at 550 degrees is lower than 10.5%. The accelerated aging test showed that after 25 years of survey at 550 degrees, the thermal emittance does not change, while the solar absorbance degradation is equal less than 1.5%. This is due to low diffusivity of tungsten used as an infrared reflector. A better photothermal efficiency could be obtained by using silver as for selective coating for medium application. Silver has a lower reflectance than tungsten in infrared region, but the higher diffusivity of silver does not allow today to grant the coating stability at high temperature. So the ENEA receiver was used in some plants. For example, solar receiver for medium temperature has been used in Dubai 1 CSP plant in Saudi Arabia that use synthetic oil as heat transfer fluid, while the solar receiver for high temperature has been used in Cassaccia in China, Mats in Egypt, and Partana in Italy. So ENEA is developing new solar coating for application at high temperature, greater than 550 degrees, with silver as infrared reflector in order to improve photothermal performance, thanks to the higher reflectance of silver than tungsten one in infrared region. Improved long thermal stability are obtained introducing a barrier layer above and below the silver layer to block the high diffusivity of silver atoms, that undermines the structure and the chemical stability at high temperature of ENEA coating with the silver as an infrared reflector. We have more efficiency surface pretreatments of stainless steel substrate and high energy sputtering process to deposit more compact and uniform layers above and below the silver infrared reflector. So now we consider some details regarding tanks, and that is the thermal energy storage. The purpose of the ventilation system for tank foundation is to prevent the concrete from reaching critical temperature to its stability. Using normal concrete, this temperature must be kept below 90 degrees. The pipes must therefore be able to remove the heat flux from the bottom of the tanks at the interface with the insulation and the concrete. So for a passive cooling system, all pipes have the same dimension, that are the same diameters and length. But for each pipe, we have different active length for heat removal. Active length decreases if we move from the center towards. It is possible to use stainless steel AZ 304 because it is not in contact with molten salt, but only with air. So there is an high efficiency and high difference between inlet and outlet cross-section to ensure a chimney effect and to enhance the thermal the heat removal. So also buoyancy for ensure air circulation inside the pipes. Another issue at the floor of the tanks are thermal stresses, because near the center of the tank, thermal resistance to heat transfer from the floor to the foundation can be greater than the thermal resistance at the perimeter of the tank. So heat flux from the floor is greater than perimeter than at the tank center. Simulation show that any radial gradient above 35 degrees is sufficient to permanently damage the floor. Okay, for the molten salt, the most outstanding problem is the significant freezing hazard due to the high melting point. In case of the solar salt, this temperature is equal to 240 degrees. So we need this high freezing temperature introduce a significant hazard of salt plug formation in the pipes in all parts of the plant, and high temperature must be guaranteed in all components crossed by the molten salt by implementation of specific heating system. The heating system are necessary for three-phase. So preheating the components before the first molten salt circulation, maintaining the temperature during the drainage phase, and melting the salt after accidental salt freezing. For dimensioning an electric heating system, we must consider obviously three different rates. That is heating, maintaining, and letting heat of fusion. So for heating thermal power, we must heat the mass of the steel at the mass of the molten salt from ambient temperature to the final temperature. So for maintaining thermal power, if we refer to a pipeline, we must compensate the conductivity heat loss through the insulation layer. And in the case of freezing, the thermal power is related to the latent heat of fusion of molten salt. We can find three common heating systems: tracing with heating cables, heating by Joule effect, and heating by armored resistance. So the mineral insulating heating cable consists of a resistive conductor insulated with the oxide of magnesium and a continuous and seamless metal outer sheet to meet different application needs and to have a range of resistivity value as much as wide possible. The resistive conductor is made of copper or its alloy, while the outer sheet can be made in copper or AC321 and Inconel C600. They can be powered both at a very low voltage on the low voltage based on the system requirements and power heaters that must be installed on the various pipes, choosing appropriate resistivity. So for the dual effect with the impedance heating, we can directly heat the pipeline by flowing electrical current through the pipeline wall. By direct connection with the power transformer, it works with low voltage but high current. In this way, the pipe has been uniformly heated, and it is best suited for long straight runs or pipe without component, but is critical for piping and instruments installed in an impedance system and they are not grounded. Joule heating is the main option used for the receiver tubes using molten salt as a heat transfer fluid, because the glass pipe makes the use of heat tracing unfeasible. So for heating a vessel, a tank, and so on, it is possible to use armored resistance, but it cannot be in contact with molten salt because it has a flange connection. A flange connection be avoided to possible leakage of molten salt from the plant. So it is better to have a welded pit, such as this, to which to connect the armored resistance. We have a picture of a practical installation. So to sum up, the use of molten salts requires certain precaution, especially if we want to exploit the full working temperature range, and above all, avoid the risk of freezing. For pipe, vessel, tanks, but also pumps and other components, it is recommended to use stainless steel AC321. You have seen the influence of the selective coating on thermal efficiency of receiver tube and consequently on the performance of CSP plant. We discussed thermal issue for the floor of the tanks, in particular passive cooling system and thermal induced stresses. And in conclusion, we have seen some electric heating system in order to ensure temperature above a melting point in all CSP plants. Thank you for your attention. Any question? Yeah. Empirical number, yeah, for present. Okay. The question is from what source is taken, and the safety factor. The numbers reported in this slide are related to practical installation. So we consider a higher power erogated from the heating system, respect then to the calculation with the semi-empiric from the formula, the results of the formula. Anyway. Okay.
You want to push up the limits, temperature limit of liquid coating. And to push up the maximum temperature.
So the state of art of ENEA receiver tube with selective coating developed by ENEA, the test reported that this layer are stable up to 550 degrees. Beyond, there is a degradation of the layer of the ceramic coating and of the performance in absorbance and the emissivity. So this way there is a lower performance of the selective coating. So with the new development, we can go beyond this limit up to 600 degrees to have good stability up to 600 degrees.
One thing say is coating as well as 400 degrees. So are there any developments in carbon steel for receiver tube? So it's enough to use carbon steel coating or manufacturing receiver. We always obliged to use stainless steel tubes.
Okay, I repeat the question also for the online participant. So the carbon steel is used only for oil, or okay. We have no experience in these topics. So with the ternary salt, it is suggested to use stainless steel. For example, 316, IC 316, but non-carbon steel.
Okay, Marco, sorry, we have a question from remote attendance. Benedetto asks us if there is any inconvenience in using dual heating systems for salts at temperatures below 300 Celsius degrees. For example, for unfreezing the source salt.
Okay. I think I don't think so, because the freeze the solar salt, it can be dielectric, so we have no issues in this way, but.
Okay, we can add in general, when you're melting the salts, the problem is that in the early stages of melting, you have a solid salt around the electric heating system, which means that you will have a high thermal resistance, and so you will have high temperature on the heating element, and you have to lower. You have to carefully and progressively increase the power supplied by the system. Otherwise, you will overheat the heating elements, and you will end up with burning and bringing them to failure.
Yeah, the electric heating can be designed opportunely to manage these critical events in the tube. Thank you.
Thank you again, Marco, for the very interesting presentation. We will have a coffee break now, so 10 minutes. Okay. We will come back soon online. Yes. At 11 o'clock. Okay. See you later.